Hello everyone, this video is designed to help you understand SR latches, JK flip-flops and T flip-flops, and also the difference between asynchronous and synchronous circuits. So the first thing I'm going to go over is what SR latches actually do. So this is an SR latch and this is an SR latch, but these inputs are activated when the input is 1, and this would be active. This, if you think of this as set and reset, so this is set and this is reset. So if you put a 1 here, this would set Q to 1 and Q bar to 0. And if you send a 1 to here, this would set Q to 0 and Q to 1. So, and Q bar is always the opposite of Q. So if Q is 1, Q bar will be 0. If Q is 0, Q bar will be 1. It's always like that. It's essentially like this. You think of it like that, it will just be the inverse or the complement of it. So, and with this, if you sent a 0 to set, then Q will become 1, and if you set a 0 to reset, then Q will become 0. And there's, in addition, SR latches do another thing where they will hold if you send 2 zeros, it will hold whatever value is on here. So if 0 and 1 are on here, are on the outputs, and you send 2 zeros, it will just remain 0 and 1. And if it was 1 and 0, then it would be the same. So you can see in this truth table, if reset is 1, then Q will become 0, Q bar becomes 1. If set is 1, Q bar becomes 1. Q becomes 1, Q bar becomes 0. And if both of them are 1, this is what's called a disallowed state. And it's on this truth table, it is essentially the inverse. So 2 zeros is disallowed. If set bar is 0, sorry, then Q will become 1, Q bar becomes 0. If reset bar is 0, then Q is 0, Q bar is 1, and this would be your hold. This will hold whatever values on Q and Q bar. Now, this moves us on to JK flip-flops very nicely, because a JK flip-flop is basically like an upgraded SR latch. It stops you from being allowed to do it stops you from sending disallowed inputs, and also has a clock signal. So I will show you how that works. Now, as you can see, I've added J and K into this circuit, and you'll see that I've left a space there. That will become important in a minute, but let's just move this table down. So now you can see that J can only be activated if Q is 0, because if Q is 0 and that means Q bar will be 1, so you'll have a 1 in this input because you can see it's connected, and a 0 in this one. So even if you sent a 1 on J and K, on both J and K, which you can't do on a normal SR latch, then it won't matter because this will pass a 1 and this will pass a 0, which means it's completely valid to do that. But all it will do is flip between the states, which is essentially what the T flip-flop does, but I'll come on to that in a minute. So, and when it sends a 1, this will become a 1. And this will become a 0. And I'm just going to rub that out for a moment. So now we will have a 0 here, because as you can see it goes like that, and you'll have a 0 down there. So now the only, you could send a 1 and a 1 again, but you don't want to do that, because if you're sending a 1 and a 1 still, all it's going to do is just keep toggling these, because it's just going to go 1 there, 1 there, and then it's going to do, these are going to change, these outputs are going to change, and then it's going to go 1 there, 1 there, and then it's going to keep changing loads and loads of times. So this is why JK flip-flops have a clock pin. That's why I've left the space here. It's usually denoted by a symbol like that, or it can be called clock. It could also be clock bar, but we're just going to go on the clock because we're using AND gates. So let's just remove all these values. Essentially, the short way of explaining what a JK flip-flop does is when you send a 1 to J, it will turn Q to 1. And if you send a 1 to K, it will send a 0 to Q, or Q to 0, and obviously Q bar is the opposite. So, but you can also send a 1 at the same time, which will toggle, as I just said, and that is the fundamental of a T flip-flop, but I will come on to that in a minute. So with a clock, the actual, let's say you're on 0, let's say you have a 0 at Q. Let's say you have, and which means you'll have a 1 here. Therefore, you're going to have a 1 on this input. Let's say you want to change Q to 1. So you send your 1 into J, you'll send your 0 into K. Well, it doesn't actually matter what K is. Then it won't do anything because your clock is still 0. This is an AND gate, so this would be 0 until you send a rising edge. So it's not just setting this to 1, this will activate on the rising edge of the clock. So say you were sending a wave, it would only activate on these rising edges of the square wave. But we're just going to go one rising edge, and your J is high. So on that rising edge, do it in a different colour. It's always good to, if you're drawing a timing diagram like this, it's always good to mark where the rising edges are. Your S is going to become high there. Well, it's actually going to become like that. And since S is going high here, your Q and Q bar are going to change from 0 to 1, and then it's just going to stay like that. And your Q is the opposite, so it's going to go like that. So that's the fundamental of a JK flip-flop. And if you wanted to change from 1 to 0 on Q, then you would send a 1, or you'd have K high at 1, and then you send a clock pulse, and that would activate on the rising edge. So a short diagram I want to draw for you is, well, you can see the JK flip-flop acts like an SR latch, but it will only activate on the rising edge of the clock, and it won't. The disallowed state doesn't matter. So I'm going to delete this. Actually, before I do that, okay, cut here. This circuit equals this. And you'll see this symbol a lot, and probably in your labs. So this is exactly the same as what this is. So you can see it has an SR latch inside it. So now I'm going to draw a diagram to show you. So you have your SR latch is your core of of pretty much all flip-flops. Then you have your JK, which you can see it added AND gates. And then there's two different types of flip-flops are made up of a JK. They're sort of upgrades to the JK. You have the T flip-flop and you have the D type flip-flop. Let's go through T flip-flops. They are actually quite simple. All your T flip-flop is a JK flip-flop. And your inputs are connected together like this. And this has the effect of, let's say your Q is 0, sorry, your Q bar is 1. And this is your input T. Because if T is 0, all it's going to do is hold whatever's in this value. Because don't forget there's an SR latch in here. And it's not going to do anything if T is 0, because J and K are 0. So it's just going to stay the same. If T is 1, however, this will cause the JK flip-flop to flip-flop, basically. This will become 1, this will become 0, on the rising edge of the clock. So I'll draw a little timing diagram. So let's say that Q bar, like in the previous example I just showed you, Q is 0, Q bar is 1. So Q is 0, Q bar is 1. And let's say that T is 0. These are just going to stay the same because T is 0. Let's say T becomes 1 here. And you can see you have your rising edge here. So when you get to your rising edge and T is 1, Q is gonna and Q bar are gonna flip flop. So Q is gonna become 1 and Q bar is gonna become 0. And it's very important to remember this only happens on a rising edge of a clock. It doesn't happen anywhere else. So let's go, and we're at our next rising edge here, and T is still 1, so they're just going to flip flop again. Don't forget Q and Q bar are always opposites. They're basically mirrors of each other. And let's just say that T goes low here, and these are just going to stay the same. So this is equivalent to this symbol. So that's the T flip-flop. Now the most interesting one, and in my opinion the most useful one, is the D-type flip-flop. So let's go onto the D-type. And the D input is going to look like this. This is a NOT gate, and it goes into J and K. And you also have your clock input as well. So with a D-type flip-flop, it's quite simple. To put it simply, on the rising edge of the clock, Q will become whatever D is. So if D is 1 and a rising edge is sent, Q will become 1. If D is 0 and a rising edge is sent, Q will become 0 and Q bar will be the opposite. So this is very useful because it basically you can memorize a bit of data, or it stores a bit of data. So I'll draw a short timing diagram. So let's say you have your clock signal and your D value, your Q and your Q bar. So on timing diagrams I always like to mark my rising edges, because that's the only thing you're really interested in. Sometimes you have, if your symbol says clock bar, which some shift registers and chips have, then that means it will act on the falling edge and it will be like that, but we're not using that at the moment. So let's say that Q starts off at 0, Q bar starts off at 1. Let's say D starts off at 1. So on the rising edge, Q will become what D is, and Q bar will become 0. Let's say D goes to 0 at this point when this rising edge is sent, Q will become whatever D is, which becomes 0. If D doesn't change by the next rising edge, Q will just stay the same. So this is a very useful gate to use. I was just gonna, and the symbol would look like this. So that's that, and you can make a T flip-flop by connecting Q bar to D. So that's going to be the end of this video, and I know I said in the start I would go over synchronous and asynchronous, but I'm going to put that into another video. So I hope you guys enjoy, and if you have any questions, just put it in the comments and I'll take a look.